Okay, so this is part 2 of my video, and I'm going to repeat myself many times, but I hope you can bear with me. So I did this video, and then Dave and I corresponded through email, and he explained something to me that I didn't understand, that I had to do a bunch of research on it, which was common mode rejection. And so it answers some of the questions I had here, but there's still some areas where I don't know, maybe we still differ. Again, not in how things work. I don't say a gazillion times. He knows everything about how things work. This is a question of explanations. How do you explain this stuff? And so, I had pointed out. I said, listen, this diagram that many like it, that I saw like 20 years ago. They never made any sense to me. And I understand what you're saying, but I think it's wrong. Anyway, I just don't. Again, I didn't. Explanation doesn't make any sense. So I need an explanation that makes sense for me. And a big thing for me is conservation of energy. You can't say, oh, well, something happens here and it doesn't end up here and I don't care about it. Like that won't work for me. In practice, yes, that works, obviously, right? So if you're just a professional and you're plugging in balanced cables from your musicians on the stage, right? And there's interference and it just disappears, like it doesn't go into your amplifier, then obviously, yeah, who cares? It came, it's rejected, it's gone. I don't care where it goes, right? But I think from me, like trying to understand it, from a physics sense or electronic sense, yeah, it does matter. I mean, it has to go somewhere. So this is another version of that diagram that's seen a million times. It basically says, okay, you have one line somehow, like this thing makes no sense to me. You have one line, you have the noise in it and the noise in the output, but somehow you have these two lines and the noise is canceled because they're both lines and it's canceled. Like I sort of understand what it's saying, but I feel that this is totally nonsense. So I've redone this so that it makes sense to me. And again, I'll be curious to see what Dave says or anybody says, but this is my understanding of the first diagram, really. It's leaving out the return line. So it's two wires. So the two wires, and yes, there's noise in the input because there's no way really to put that noise anywhere else. And the second part, what it's really leaving out, so pin 2 and pin 3 is what I'd say are the main mic lines that go to the black sine waves that you're seeing there. And what it's leaving out really is that the noise, although it's in the two main lines, pins 2 and 3, it's in the mic line, a transformer, a choke transformer, ignores them, like this is it's hard to get it a language, but it doesn't allow it to flow through this interference. And so I'll get to this a little bit later. So it basically forces it all out through the first pin cable, the ground cable. Now, some goes away through heat or through electromagnetic radiation, whatever. So, a big question I have is like, okay, if you say is a lightning strike, and let's just say that the 100-volt thing gets into both wires, right? Which is what Dave talks about. Like, okay, well, that doesn't mean if I touch it like 10 minutes later, I'm going to get electrocuted. No, well, why, right? Because it has to go somewhere, and I believe that place it goes is the ground. And this, anyway, this doesn't. This is how I think it works. Okay, and I'll repeat this in a couple different ways. So now, here's the slide I did yesterday, where I said, okay, so you have what I don't get is you have these, you have the balanced line and lightning hits it, right? So I'm saying that the incorrect balances cable theory claims there's a phase on the positive wire that can be isolated and circuit removed. And I'm saying, well, how would I see that behind my wall when Kirchhoff says both wires are equal, right? So if interference hits your mic lines, right? Like how am I going to see it? It's just, all I see is the voltage coming out. How can I separate the lightning voltage from any other voltage? I just don't get it. And this is where through email, like Dave went back and forth. I'm sure it was very exhausting for him. But anyway, through his explanations and my research, I think I understand now what's going on. Though again, this might be, I don't know, maybe this is wrong too. So I think what needed to be explained is that essentially the lightning is on a different circuit. It's on like a floating circuit, a ghost circuit. It's both in the lines of the microphone lines, but it's also sort of in its own like loop, its own, and again, we sort of get into differences on what you call ground you know, anyway, but it's in a sort of own separate circuit. So I need to think about a circuit because again, I need Kirchhoff to apply. I can't think about half a circuit because he says there is no half a circuit. Any circuit, both wires are equal. So I can't think. I need to think of the lightning as part of a circuit. So I think there is a circuit, and but it's not a circuit when it hits the lines. It's just like a positive voltage, but it's an implied circuit. So again, it's hard to explain this, and but this is just what works for me. Thinking about it as interference as a second circuit, so that it doesn't violate the law that Kirchhoff says about the primary mic circuit. And so here's what I had from yesterday, and I believe this is still correct. But I didn't understand one part, which again, Dave explained to me. And that part is the transformer that will sit between the mic output and the input to the amplifier. So this is what rejects common mode noise. And I'll get into explain to it in just a little bit. And then here again is that diagram where I did specifically with the microphone. Again, you have a choke transformer sitting between the line of the mic and the amplifier, and it rejects the interference. But I do want to say, I still say, there's no difference between XLR cables and regular cables. I mean, XLR is just a type of way they're pinned and putting an adapter. Balancing does not happen in the cables. Balancing can happen in any kind of cables. But that said, I don't want to say cables don't matter. They do. So, Dave's an expert in this, and he has a company that sells things that test cables. So, if you have an XLR cable and you want to run balanced audio, well, this thing will help you check out the cable to make sure you can actually do that common mode noise rejection or whatever. So anyway, so how does a transformer work? So a transformer is made of a single magnetic core, usually a ring of magnetic material like iron or ferrite. Two separate coils of wire wrap around different parts of the shared core. This is a choke type. So the way this works, you'd have the microphone going in here, coming out here. So when the microphone current goes through these wrapped wires, it creates a magnetic field. And as you know, you can switch between magnetic fields and current to magnetic fields. So it creates a magnetic field, and then the other end, this wire converts that magnetic field coming from here into a current again that's replicating the microphone. So the whole idea, it takes the signals and cancels out. Again, I don't know, I'm not gonna go down that road. So anyway, that's what this does, okay? So one coil connects to the primary winding, the other coil to the secondary winding, to the our amplifier. Now here's a sort of a diagram of this. And so if we talk about it working in a normal way, which is a differential mode, and this is another thing I didn't quite understand. I think I did understand it, but anyway, the current of the microphone, it doesn't really make a difference what the voltages are, whether it's 1 volt, 3 volts, or 1 millivolt, or whatever. What's important is the differentiation of volts, right? That's really speech and audio, right? It's not just we hear in tones, we hear in sine waves, we hear from plus to minus, right? Or sound pressure to no pressure, right? We hear the differences. So in the differential mode winding of the choke, what happens is you get as Dave pointed out in his video, you have one line that has a positive voltage, another a negative voltage, and they both are equal in different directions. And you add them together and they cancel out. So you have this going, so it goes through this, and it creates this magnetic field, and then it goes into the other system in the same way, right? So you basically have a loop of the differential mode, well, the microphone signal, essentially. But okay, so let me just explain more. So yeah, the mic's voltage causes current to flow through the primary winding. It creates a changing magnetic field in the shared core. This changing field induces a proportional voltage in the secondary winding, which comes to the amplifier. So wrote out what I just said. Oops, okay. Now in common mode interference, what happens is both lines get the same voltage or push, let's say from a lightning bolt. And what happens is they don't create a magnetic field that is picked up by this method, because again, this really works with alternating voltages, essentially oscillating voltages, from a microphone or something like that. And so because of it, it basically pushes it to ground. And you can see that if you look at both graphics. On this graphic, where it's talking about differential, there's no ground thing there, and in this there is, which is what I drew up above. So the important aspect to understand is that the transformer doesn't react to the absolute voltage of the wires, as I said. Instead, it responds only to the differences in voltage between the wires. The transformer only, sort of sees these differences, and not their absolute levels. And this is what Dave shows here. The top is positive, and the bottom is negative. So again, the microphone creates an audio signal where its voltage oscillates up and down relative to ground. When this hits the primary winding of the transformer, one wire swings above ground, positive, the other wire swings below ground, negative. The voltage difference between the two wires represents the audio signal. So again, I know I'm saying this multiple times over and over again, but we have a circuit, it's in the microphone, and both wires are going up and down with the oscillation or vibration of the microphone. Interference, however, is different. So it creates a wave that shifts both wires' voltage up and down together relative to ground. Now again, this is where Dave and I had a problem. I'm saying, yeah, to me it's like relative to earth ground. He's saying, well, no, not really relative to anything. It doesn't make into the system. But I think it's easier to think about it as relative to ground. And be curious to see what he says. So it's like the wires are floating on the interference wave. However, this common shift doesn't affect the voltage difference between the wires, which means the transformer does not respond to it, right? The magnetic coupling in the transformer core reacts only to relative motion between the wires, not their absolute positions relative to ground. So it doesn't care if, like in the wires, let's just say you have a wire that's swinging between 1 volt and a negative 1 volt from the microphone. It's going back and forth, let's just say in 440 hertz or whatever, right? So if you get a lightning strike and all of a sudden you get like 100 volts going through the wire, it doesn't, if it's just 100 plus volts, it doesn't, the transformer will not create a magnetic field for that. It needs a difference of volts or current to create a field. And this is what Dave shows in part of the video. So the interference energy doesn't vanish or persist indefinitely in the wires. It is physically dissipated or redirected depending on how the circuit is constructed. And that's what, one of my main things. Again, the lightning hits a wire and in 10 minutes I touch it. Why don't I get electrocuted? So the transformer contributes by isolating voltages, preventing currents, like from the lightning strike or electrical interference, in the shield from coupling back to the audio signal. So in a sense, the transformer is helping to work to keep the two circuits separate, right? The one circuit, which is from the microphone, coming in, and the other circuit, which is the ground wire, which although it's one wire, in a sense it's two wires because it does complete a circuit with the earth, but you only need one wire, right? And I went into that in yesterday's video when I was talking about, the early telegraphs. In the early telegraphs, it had one wire because it used earth as a common return for everything. So, and I didn't mention in that video enough that, so in the telegraph, in a sense, like instead of swinging two wires between two telegraph, places, you'd have one wire, and then the one wire would go into the ground in each place, but the ground would serve as a wire between them. So earth served as like that second wire. And it's the same thing in these balanced audio cables, right? The pin 1 wire, the ground wire, in a sense, it implies a second wire. You just don't see it because it's using earth as that wire. Okay, so the inference flows to ground via the ground wire or shield, which serves as a sink for unwanted energy. Part of the energy dissipates as heat in resistive elements along the path to ground. So if it doesn't go through the cable, it might just, again, sort of like just make a little heat and disappear that way. Again, all energy has to be accounted for. So all the interference, you can't just say, oh, this doesn't go, it doesn't go, and it gets into my line and then disappears. So a portion may radiate as electromagnetic waves, depending on the system design and frequency of the interference. And actually, this is a problem, right? Because all voltages can create magnetic waves, and all magnetic waves can create voltages. And this is, I think, the prime problem of all audio engineering, right? Is keeping these things separate and not letting one generate another that screws everything up. So the balanced design ensures that common mode interference affecting both wires equally is rejected, preserving the integrity of the audio signal. And so that's it. So anyway, that's where I'm at, trying to put David's explanation in my own words in a way that I understand it. Hopefully this is right. I look forward to comments of any of you that have something to add. Thanks for listening, watching.